Well, welcome back to the lesson 22-3 practice on page 314 in Springboard Geometry. We just covered lesson 22-3, so let's take a look at the practice. So item 7 says find each unknown side length. So notice in item A, we are given the measure of an angle in a right triangle, 18 degrees. And also the length of one of the sides. Now, it's very important that we know that this side that they give us is actually the hypotenuse of this right triangle because it's opposite of the right angle. So we are given the hypotenuse. Let's make sure we know that. And we are tasked to find the other two legs only given one other side. So we are not using Pythagorean Theorem here from the get-go, although once we find one of these other two sides, we can use that to find the other length. So clearly we should be using one of our trig functions. Now, more than likely, you're going to use this 18 degrees, but those that like to dive in a little deeper, if you feel the need to go ahead and find this other acute angle and utilize that one to write your trig functions, go right ahead. But I'm just going to use the one that they give us here. So let's solve for x first, I guess because it's first in the alphabet. So in reference to this 18-degree angle, x is our adjacent side, and we are given the hypotenuse. So which trig function uses adjacent and hypotenuse? Hopefully you're answering cosine. So the cosine of 18 degrees is the adjacent side x over the hypotenuse 25. Now I'm going to find the approximate value for the cosine of 18 using my Desmos calculator. So I encourage you to do that as well. So the cosine of 18, and just like we did in the book, we're going to use the thousandth place, which the 1 is in the thousandths place, and we look to the 0 right behind it to tell us that that 1 will stay where it is. So we're going to replace cosine of 18 with 0.951 equal to x over 25. I like to rewrite this side as a ratio because this is already a ratio. And they are supposed to be equal ratios. So let's write this over 1 and then cross multiply. And we will get x equals to 25 times 0.951, which is rounded to the nearest tenth. I see it's 23.775, so we'll say 23.8. So the length of x is 23.8. Now, those of you that want to now work on the Pythagorean Theorem, go for it because we now have the approximate length of this side x. But notice what I just said, we're using the approximate value here. Now, granted, cosine of 18, we're also using the approximate value. I'm going to use another trig function because that's what this lesson is about, to find the length of y. So the length of y is the opposite side of our angle that they're giving us, 18 degrees. And we were definitely given the hypotenuse, so I'm going to use the sine of that 18-degree angle. So the sine of that 18-degree angle to now find the opposite side, which is y, over the hypotenuse 25. Now I'm going to find the approximate value of sine over a sine of 18 degrees. So let's just do that now. Sine of 18. I see that the 9 is in the thousandths place and there's a 0 behind it, so it would be 0.309. So I'm going to replace sine of 18 with 0.309 equal to y over 25. Write this left side as a ratio by writing it over 1 and then cross multiply because I just created a proportion. And very simply, I will get y equals whatever 25 times 0.350 or 309 is. Which I see is 7.725, so rounded to the nearest tenth, we get 7.7. And hopefully you find that same value if you actually use the Pythagorean Theorem here. So now what I encourage, now that you saw the process for 7a, try 7b and 7c on your own before playing through the video. Okay, so The first thing I want to say, and this is just like our proportions with similar triangles, there's no one way to do this. So be encouraged if you found a different method to do this other than the trig functions I use, please know that as long as our answers line up, we're in the clear. So I assume most people use that 72-degree angle, and in reference to that 72-degree angle, we have the adjacent side 8.5, and we're looking for the opposite and the hypotenuse. So if we have the adjacent, I thought it'd be kind of interesting to use the tangent function, because we haven't really used that one much, to find the opposite side, because the tangent function says compare the opposite side to the adjacent. So that work is actually way up here. So the tangent of 72 degrees is opposite what we don't know over the adjacent we do know. And so I found the tangent of 72 roughly was 0.3778. And so I replaced with tangent of 72 with 3.078. Let me just make sure I did that. Yeah, 3.078. Cross multiply, put this over 1, cross multiplied, and found that x equals 26.2. Well, again, you could use Pythagorean Theorem because now you will have two sides of this right triangle, and you could find the hypotenuse using the Pythagorean Theorem. But I wanted to keep in line to what this lesson is all about. It's these trig functions. So now I'm trying to find the hypotenuse, and I was given the adjacent. So I decided to use the cosine of 72 because the cosine function compares the adjacent side to the hypotenuse. And that work is done here. I found the approximate value of cosine of 72, and it was 0.309. So I replaced cosine of 72 with 0.309, cross multiplied, and had to divide even here, and found that y equals 27.5. Now, item C, something really caught me off guard. So I just started working this problem like normal. Didn't even think about the fact that this was 45 degrees and said, well, in reference to this 45-degree angle, this side is opposite of that. The 34, the measurement that's given, is opposite of that 45-degree angle. One of the sides I'm looking for, x, is adjacent to that 45-degree angle, and the other side I'm looking for, y, is the hypotenuse of that right triangle. So again, I thought, I have the opposite. X, what I'm looking for is the adjacent side. Why not use the tangent? The tangent function compares the opposite side to the adjacent. So I started this equation. The tangent of 45 is equal to 34, the opposite side I was given, over x. And when I went to put in the calculator, this is where the realization came to me. The tangent of 45 is 1. And then I noticed I was dealing with one of our special right triangles, the 45, 45, 90 degree triangle. And so I realized that if this side is going to be 34, one of the legs is 34, the other leg has to be 34, because if we have two congruent angles in this triangle, we're going to have two congruent legs in this right triangle. So without actually even solving, which you could see the work here, 1 equals 34 over x, 34 over what is 1? Well, it would be 34 over 34. But we could also remember that we have our special right triangles to find that missing side as well. So if we think back to our 45, 45, 90 triangle, we know that the two legs are going to be the same length, and whatever the length of the leg is, the length of the hypotenuse times the square root of 2 is the length of the hypotenuse. So if you notice, I actually wrote that here for y. So if the length of the leg was 34, then the hypotenuse is 34 times the square root of 2, which if you put that in the calculator, you get approximately 48.1. But since maybe we forgot that that was a special right triangle, maybe we forgot the ratio to the leg to the hypotenuse of that triangle, I wanted to show you that you can still find it using the trig functions here. So if the goal is to find y, which is the hypotenuse, and we're given the opposite, why not use the sine of 45? Because we would have the opposite and we'd be finding the hypotenuse. So the sine of 45 is equal to 34 over y, the opposite side over the hypotenuse. I went ahead and evaluated sine of 45 to be roughly 0.707, again rounding to the thousandths place. So I replaced sine of 45 with 0.707, wrote that over 1, and then it cross multiplied. Now here it was 0.707 times y, so I did have to divide as well. And when I divided both sides by 0.707, I found y is still 48.1. So both methods are actually usable here. Just like on these other two, we could have used Pythagorean Theorem. So there's so many methods we're learning. Similar or special right triangles, Pythagorean Theorem, trig functions, similar triangles. I know there's a lot in our head. It just all depends on what's given to us. So that's primarily why we're focusing on the trig functions here, because we're only given an angle measure and one side. Now let's continue on our practice. So if you notice, item 8 actually says reason quantitatively. Quantitatively means with numbers. So we're going to be reasoning with numbers here. And I love that the actual into this item says be sure to check that your answers are reasonable. We need to, as we're solving these missing sides, to evaluate and understand, are these numbers making sense, right? If this hypotenuse is 15 feet, well, then the length of these two legs should not be greater than 15 feet. So kind of use the things we've learned and some of the properties of these right triangles to help make sure that these answers are actually reasonable. So Jackson has the triangular garden shown in the figure. Our first task is to find the perimeter and then the area of the garden. Now, remember, perimeter is the total distance around a figure. So we need to find all three sides, and then area is the amount of space that the entire figure takes up. So two different things. Let's first start by finding the perimeter. So we need to find these two sides. In fact, these two legs. So we'll call this one X and we'll call this one Y just for the sake of the problem. So in reference to the 22-degree angle, I've been given the length of the hypotenuse, 15 feet, because that is opposite of the right angle. So I'll go and label that this is in fact the hypotenuse. So we have to find the adjacent side to that 22-degree angle and the opposite side to that 22-degree angle. So hopefully you're thinking of the sine and cosine functions. So if we're solving for x first, x is the length of the side that is adjacent to the 22-degree angle. So I'm going to start with the cosine of 22 degrees because the cosine function is defined as the adjacent side over the hypotenuse. So cosine of 22 degrees is equal to our adjacent side x over 15. We're going to find the approximate value of cosine of 22. So let's take a moment to do that. So I'll go and close out these and type in cosine of 22. I see that 7 is in the thousandth place, and the 1 tells the 7 to stay where it is, so it would be 0.927. So I'm going to replace cosine of 22 with 0.927 equal to x over 15. Write this left side as a ratio, and then cross multiply. And with one step, we find that x is equal to 0.927 times 15. Which I got 13.905. So we'll say 13.9 because they didn't actually tell us to round anything. So we'll just assume to the tenths. So we found the length of this side to be 13.9. Now we have the option to use the Pythagorean theorem here to find the length of this third side. But again, because we are in this trig function lesson, I think it might be wise to just go and keep using the trig functions to get good practice with those. So in reference to the 22-degree angle, side y is the opposite side. And again, we were given the hypotenuse, so I'm going to use the sine function. So the sine of 22 degrees should be equal to the opposite side y over 15. So I'm going to find now the sine of 22, which again, it's not the same as the cosine of 22. Remember, it's the sine and cosine of complementary angles that are, in fact, equal. So the sine of 22 is 0.3746. So the 6 actually tells the 4 to round up. So we will be dealing with the approximate value of 0.375. So the sine of 22 will be 0.375 equal to y over 15. I'm going to rewrite this left-hand side as a ratio so that we can cross multiply and find that y is equal to 0.375 times 15, which is 5.6. So now we know the length of this side is 5.6 feet. And I'll add the little tick mark there, the little apostrophe to represent feet. So we need to find the perimeter. So perimeter is the total distance around the figure. So we will add these three measurements here. So I'll put that work, I guess, over here, although I'm running out of room. Perimeter is 5.6 feet plus 13.9 feet plus 15. And we get I got 34.5 feet. So that is perimeter. Now we need to find the area. So the area formula for a triangle is 1/2 base times height. The issue is we actually have three measurements. So how do we decide which measurements are the base and which one's the height? Now we often think the base is the bottom and the height is what goes up. Not always the case, because if we notice on these examples, they're all twisted and turned and rotated. So we really need to define clearly what the base and height of a right triangle is. Well, if base really means the bottom and height really means a vertical distance, the base and height are the two sides that make the right angle. The base and height are the two sides that make the right angle. Because if you think about it, we could actually view this as a rectangle, and that's the two measurements you would multiply by. But the problem is it's not a rectangle, it's half of a rectangle. That's why we use the formula of 1/2 base times height. So area here will be 1/2. We could call this leg the base, 13.9. Oh, let's add the 1/2 first. So 1/2 times 13.9 times the height, which is 5.6. Again, the base and height for area of a triangle are the two legs, the two sides that make the right angle. So now let's calculate the area. I got 38.92, so we'll round that to the nearest tenth, which would be 38.9. And remember, perimeter is different than area. Perimeter is the total distance around the shape. So we leave it in the units that we're given, 34.5 feet. But area is the amount of space that figure takes up. And we actually measure area in squared units. So area of this triangle is actually 38.9 feet squared, or you could write squared feet. Don't have very much room for number 9, but we'll take a look. The longer diagonal of a rhombus measures 20 centimeters, and the rhombus has an angle that measures 100 degrees. Determine the perimeter of the rhombus to the nearest tenth and explain how you found your answer. Now, perimeter here, just like perimeter in the last one, is the total distance around the figure. So a rhombus is a diamond shape. So our task is to find all four sides of this rhombus. But the great news about a rhombus, if we know the properties of a rhombus, is that all four sides are actually congruent. So if we can find one of these sides, we can add that measure 4 times or simply multiply it by 4 to find the perimeter. So let's talk about the information they give us. In a rhombus, there are two diagonals, one here and one here. Now they tell us that the longer diagonal is 20 centimeters. So I'm going to assume that this one right here, just the way I drew it, this is 20 centimeters. And then they also tell us that it has an angle that measures 100 degrees. Well, looking at the way I drew the diagram, and again, it's a rhombus and it's a rough sketch, this angle right here and this angle are actually going to be the 100-degree angle because they would have to be the larger of the two congruent angles in this rhombus because they're opposite of the longer diagonal. So these would actually be my 100-degree angles here. And if you didn't know this, all four angles in a quadrilateral have to total 360 degrees. So with that said, if these two angles in the rhombus are 100 degrees, then these two have to be 80 each. So again, these two will be 100 degrees because they're opposite of the longer diagonal. So if you can't tell, what we actually have right here is a right triangle. So I'm going to pull that out and just make it a little bit bigger here. And now this leg of that right triangle is half the distance of that longer diagonal, so it's 10 centimeters. And this measure right here, which was actually half of this 100-degree angle, that is going to be our 50-degree angle. And remember, our goal is to find the perimeter, so we need to find this side that actually represents one of the sides of the rhombus, so the hypotenuse here. So we're given just one measure of one of the sides of this right triangle and an angle measure. So we are going to use a trig function to find this side. So this side of the right triangle is the hypotenuse. So we will more than likely use the sine function because I see we're given the opposite side and we're looking for the hypotenuse. So the sine of 50 degrees is equal to the opposite side, which is 10 centimeters, over the hypotenuse, which we'll call x, because we just don't know the length just yet. So now let's go evaluate the sine of 50 to the nearest thousandth. I see that it's 0.766, so we'll replace sine of 50 with 0.766 equal to 10 over x. I'm going to rewrite this left side as a ratio by putting it over 1 so that I can cross multiply. We'll even have to do a little division here, and I'm really running out of room. So I get 10 equals 0.766x. So again, to solve for x here, if this is 0.766 times x, we're going to divide both sides by 0.766. And I'm going to just take this math right over here. And I get that x is equal to roughly 13.05. But they did tell us to round to the nearest tenth. So we'll go and round to the nearest tenth here. So the length of this hypotenuse, which is one of the sides of our rhombus, is 13.1 centimeters. So again, all four sides of the rhombus are congruent. So to find the perimeter, we'll take this measurement, one of the sides, and multiply it by 4. Which is 52.4 centimeters. So that is the conclusion of the lesson 22-3 lesson practice. Hopefully that helped for those that are still struggling with determining which trig functions to use. But again, go back, rewatch, rework, whatever you need to solidify how to use these trig functions. Thank y'all for watching.